um, Max from Hamburg University. He will tell us about lifting theorem for Grothendieck-Verdier categories. Max.
Thank you for giving me the opportunity to speak here and organizing such a nice event. And thank you all for coming. I will talk about results that were mainly obtained during my master thesis with Christoph Schweigert. There's more recent work on generalizations of Frobenius algebras, Frobenius-Schur indicators, coherence theorems in the context of Grothendieck-Verdier categories. I will try not to talk about this today. Instead, I'll try to talk about the lifting theorem for Grothendieck-Verdier categories. And my talk has three parts. So first I'll tell you what Grothendieck-Verdier categories are and why I care for them. Then I'll seemingly take a detour and talk about generalizations of Hopf algebras known as Hopf monads, Hopf algebroids. And then in the last part, I'll fulfill the promise of the title and present the lifting theorem and then apply it to Hopf algebroids and Hopf monads. But let's start in the beginning, namely with Grothendieck-Verdier categories. And I want to give you a very simple example. And if you think this is too simple, then I've achieved precisely what I wanted. Because I think that with these examples, you can see quite a bit of the structure that is present on Grothendieck-Verdier categories. Okay, so we start with a algebra K, algebra A over a field K, and look at its category of bimodules. Of course, hopefully we all know that this carries a monoidal structure, which is defined as this co-equalizer. And I mean, this is defined as a co-limit. So the tensor product that we obtain is right exact. Now, Grothendieck-Verdier categories are some sort of duality structure on a monoidal category. So if you think categorically, it shouldn't surprise you that we now assume we look at finite dimensional bimodules. Look at a finite dimensional chi-algebra. Okay. So for any bimodule M, we can look at its k-linear dual bimodule, chi-linear dual as a vector space, and this becomes a bimodule by this action. Now taking a bimodule M and mapping it to its k-linear dual bimodule, this gives you a functor, a contravariant functor on the category of finite dimensional bimodules. In fact, this gives you an equivalence where the quasi-inverse can be chosen to be the functor D itself.
Did you define Grothendieck-Verdier?
Not yet.
I'll
give you an example and then I'll tell you, okay, this is a Grothendieck-Verdier category, and in this simple example, you see the structure right. Nice. Okay, so we have this duality functor D, and this induces now a second monoidal structure on our category, which is given by this De Morgan type formula where D is, you can think of as negation, and then this kind of looks like the De Morgan law that you know from logic. And by abstract nonsense, this tensor product is left exact. You can also realize this via an equalizer diagram, and then this is just a co-tensor product with pi comodules. Okay, and now the question is, okay, how can we more categorically describe this duality structure on the category of finite dimensional bimodules? Okay, and as a first guess, we might think, okay, this is maybe rigidity. And I mean, rigidity was mentioned a few times. I was thinking that also probabilists would be in the audience, but since I think this is not the case, I don't need to recall this notion, but I'm claiming that the category of finite dimensional bimodules is not rigid. And maybe can someone give me a one-sentence reason why this cannot be? I know that for some people,
I mean, the tensor product will be exact.
Yes, exactly. So in general, the tensor product of bimodules is not exact. You can, for instance, think of dual numbers. I mean, this is probably one of the simplest examples you can think of. Okay. So we need another notion, and this leads to the notion of Grothendieck-Verdier categories. And now I can give you a definition, and maybe in your mind you can try to ask, in the case of finite dimensional bimodules, what these structures and properties amount to. Okay, so we are given a monoidal category C, and then we can look at an object. Then we say that an object K in this category is dualizing if it satisfies two properties. So first, we require that for every object Y and C, the following functor is representable. What is this functor? So we take the object Y that we started with, and then we multiply it using the tensor product with X, and then we take this profunctor of form into the dualizing object, and the corresponding functor should be representable. So we should have a natural isomorphism. So we should have an object dy like that, such that there exists a natural isomorphism like that. Okay. And now representability, this representability condition implies functoriality. So by one, we get a contravariant functor d on our category C, and we require this contravariant functor to be an anti-equivalency. Okay, and now we call the pair of a monoidal category together with a dualizing object the Grothendieck-Verdier category. And this terminology goes back to Boyachenko and Lindfeld, but I mean, these Grothendieck-Verdier categories have been around for quite a while. So Mike Barr, I think, called them star autonomous categories and looked at them in the context of topological vector spaces, for instance. People in the linear logic community have also been interested in that. Okay. Okay, so we have GV categories. Maybe let's discuss examples. So I said Grothendieck-Verdier categories generalize rigidity. So we have rigid monoidal categories which give you examples, and in some sense this picture is lying to you because yes, the monoidal unit is a dualizing object, but the set of dualizing objects for a monoidal category is either empty or it's a torsor over the Picard group, meaning that dualizing objects are unique up to tensoring with a tensor invertible object. Okay. Of course, we have finite dimensional bimodules also as an example, and yesterday there was the question whether how is CP rigidity related to Grothendieck-Verdier categories, and I mean, all bimodules are CP rigid, but there's no, so the set of dualizing objects for all bimodules is empty. Okay. Then there are various other examples, but in a sense, this is a very simple example. And to the other extreme, you have a rather complicated example, namely large classes of categories of modules over the vertex operator algebra also give you examples of Grothendieck-Verdier categories. And I think this warrants a small remark to give a bit more conditions for what classes of VOAs and module categories this, or categories of modules this holds. So if we have a VOAV and we have a category C of modules over that VOA, and we assume some conditions on this category of modules and the VOA itself. So we assume that the Huang-Lepowski-Zhang theory of tensor product applies. I mean, this, and that the category is closed under taking the grade-wise dual of a VOA. Then this category of modules, together with the contragradient dual of the VOA itself, considered as a regular module of itself, this is a Grothendieck-Verdier category.
Can you say more about the C? I mean, it doesn't need to be, it's not necessarily finite, right?
No, not necessarily. Yes.
Can you say better?
I mean, C2 cofinite is, for instance, one condition.
Yeah.
And you can look at n-gradable modules, I think. Yes.
Yeah.
This would be one.
And outside of finite setting, what kind of categories you get?
So, I mean, there is in the paper, I think there's also the mention of
what category?
Feigen-Fuchs boson is discussed there. I'm not sure. So, yeah. I mean, do you want to say more about this, or do you have something in mind you want to say?
You can say more about this. Like,
is this
they have to be locally finite, or like, I mean, what? Because I mean, this doesn't say much about category C.
Yes, I mean, in general, I mean, I have no reason to expect them to be finite, but I mean, if you have specific examples in mind. I've not worked explicitly with VOAs, but
I mean, also so far the categories that he's looking at this is really a set theoretic category. Yes. It's not talking about the linear setting. And something that is very subtle is that but for this theorem, they don't make so many statements about what the underlying linear category would be, even if somehow this were in a linear setting. So it's not clear, for instance, that the underlying category here would be a finite category in the sense of Etinghoff and Ostrich. There's very little reason for that.
So no, but the finite categories are examples of this, right? C for C2 cofinite. So C2 cofinite is example.
I'm not so sure whether this is so I'm not sure whether it's actually written up somewhere that if V is C2 cofinite, that the underlying category C here would be finite in the sense of Etinghoff and Ostrich with enough projectives, finite length for every object, and so on and so forth. I think for a lot of examples this is true, but I'm not so sure whether this is generally known. I asked Simon Wood about it. He told me that for W2,3, it's true.
Yes, yes. I say there is no statement if you consider reasonable class of
Yeah.
modules that it's finite
He
category.
told me that maybe if you could,
Oh,
yeah, that maybe there's a proof, but I'm not so sure whether this is really written. It's not trivial.
mhm. Yeah. So yeah.
Okay. So we have seen more or less two examples of Grothendieck-Verdier categories. And I mean, the bimodule example is in some sense a good test case if you want to prove statements about Grothendieck-Verdier categories, while the VOA example, at least to me, is not. So you might think, okay, maybe we can construct more examples of Grothendieck-Verdier categories. And one thing you might think about is, well, how do we, for instance, produce examples of good rigid monoidal categories? As you can look at a Hopf algebra in a braided rigid monoidal category, and then look at its category of modules or representations, and then, yeah, this gives you examples of other rigid monoidal categories, and you might try to do something similar here. And more generally, what you might try to do is you have a Grothendieck-Verdier category D, you have another monoidal category with some properties, and then you have a functor satisfying some conditions and endowed with extra structure. And you can ask the conditions, okay, how can we maybe lift the Grothendieck-Verdier structure from D to C? And I mentioned functors, so we need to somehow ask, okay, what class of functors do we want to look at? Okay, the first observation is, okay, any Grothendieck-Verdier category is closed with internal Homs. And here are explicit formulae. They should remind you of these De Morgan type formulas that I showed to you before. And indeed, that there is a second tensor product on a Grothendieck-Verdier category. This is on the category of finite dimensional bimodules. This is no coincidence. I mean, it's holds for any Grothendieck-Verdier category. And these internal Homs can be used to define the second monoidal product. And these lead to the notion of linearly distributive categories with negation, or LD categories with negation. And I don't want to give you the definition, but I know that some of you have heard of them, and I'll mention them at a few places later. So I just want to name drop this here. Okay, but for reasons, since this is the notation that people in the logic community use and in computer science, and also because it's takes less space, I will use this symbol to denote the left internal Hom, and the other symbol down here to denote the right internal Hom. Okay, we need a second observation, which is in some sense rather trivial. So we have two closed monoidal categories C and D. We can look at the Lax monoidal functor from C to D. Now, the multiplication morphism of this Lax monoidal functor, this induces natural transformations of the following form. I mean, if you, for instance, take the top line and take ux to the left-hand side, then you can, using the adjunction, then you can take the multiplication morphism, pull x into u, so that you have ux o times x internal Hom y, and then you use the evaluation. And then
write something. It's hard to follow.
Okay, sorry. Should I write it down?
Yeah, would be, I think, easier to understand.
Okay. So, I mean, by adjunction, the top line, it suffices to specify a morphism that's correct. By adjunction, I mean, that's the
I'm not
definition
used
of
to
the
your
internal
notation.
Hom.
Can you write it
I
more
mean,
precisely?
this means left internal Hom.
Yeah, which you defined via, maybe you can write, because
Okay,
I don't
so
see it, because
the functor
too fast.
x o times is left adjoint to this one.
Okay. But maybe you could write somewhere, because it was on previous slide, for internal Hom formula.
Okay, yes, so, okay, so the left, the formula, I mean, in terms of duality functions.
Yeah, yeah, of course.
Yeah, okay. So the left internal Hom x and y is defined, and now let's see. So it's d, x is contravariant, so we should have So in this case, since, I mean, it's the convention of left and right, but it's d minus 1 y times x. And the other one is
Okay, yeah, so this notation is for left column. Sorry, explain again. So, the multiplication
so,
work
this is
of
the
u
same thing as just as a symbol. You can also do
Right.
and this one.
Okay, so what is the statement now?
The statement now is that if you have a Lax monoidal functor,
Uh-huh.
the multiplication morphism of your Lax monoidal functor,
Yes.
this induces a natural transformation of this one.
Induces natural transformations.
Yes.
These two.
And this is by adjunction. I mean, this is so to give such a natural transformation is equivalent to give a natural transformation of this form, right?
So you want I'm a little bit confused with x and y. Ux was moved over to the left with the maybe a junction was written below.
Excuse me?
Maybe it's not important.
Yeah.
But you wrote that tensoring on the left is left adjoint to internal Hom with the dot on the right.
Yeah.
And then the blank has the question mark on the right. But
Yes.
in this formula, Ux, Uy is on the right. And then Ux traveled over to the
No, this is correct. I mean, this is correct. Why should this be correct?
If I take this tau L
Yes,
and I apply the adjunction,
yes. Then I get a morphism, I guess.
There is confusion about what is the domain and codomain of internal Hom in this notation, and the codomain is always pointed by this circle. So the codomain is on the left-hand side of the internal Hom in this notation. In the latter case, maybe this
The
is
contrarian part is there where you don't, when not, the circle is not. The covariant part is where the circle points to.
okay.
Yeah, I think I should have stated the notation of representation theorists. Okay. So this induces these natural transformations, tau L and tau R. And if these are invertible, then we call the functor, the Lax monoidal functor U between closed monoidal categories, we call it closed. And we'll see examples later. Okay, and now we come to the main player that we need for the statement of the lifting theorem. Namely, if we have closed monoidal categories C and D, we have distinguished object, and the distinguished object K and C and small k and D, then what we call a pre-GV functor for the pair KK consists of a Lax monoidal functor between these closed monoidal categories, a morphism from UK big K to small k, such that some composites are invertible. And if you have a trouble parsing this definition, I mean, to give you intuition, so a Lax monoidal functor is something like an algebra. This, and I will make this precise in a second, can be thought of as something like a form or a Frobenius form. A form, and these conditions then say that this form is in some sense a Frobenius. Okay, and what are these conditions? So we take U, we apply U to the internal Hom into the object K. Later in the GV context, this is precisely U, duality functor, and then X. Then we use the transformation that we saw on the previous slide, tau L.
So the dualizing object was K, or
So
what
far,
was your dualizing
we're not
object?
speaking about dualizing objects. So far, we have just distinguished objects in C.
But you denoted dualizing object, you denote same letter K.
Yes, but and if I look at the definition, I'm not saying that K is a dualizing object. Right? This will become important because, I mean, in order to make sense, we want to show that K under some conditions is a dualizing object if small k is. But at this point, no, K is not a dualizing object. Okay, this works for any distinguished objects K and C, big K and C and small k and D. Okay, so we use this transformation to pull out the internal Hom, And then to UK, we apply this Frobenius form, and then we arrive at this object. And we, of course, can do the same thing for the right internal. Okay. This is just a definition. And now to your question, Azad. So in case that K is a dualizing object, both K's are dualizing objects, then we call this pre-GV functor for this pair, KK, a GV functor. Okay. So maybe examples, so a very simple example, if you have a morphism of finite dimensional K algebras, the restriction functor of bimodules gives you such an example where this Frobenius form is just applying the duality functor to this morphism of finite dimensional K algebras. More different lanes, so any closed monoidal functor between GV categories, if the unit morphism is invertible, is of course gives you an example. I mean, then all the conditions before are trivial. Now, if we have two rigid monoidal categories, this is maybe the framework most people are familiar with, then a GV functor from C to D corresponds precisely to something which is called a Frobenius monoidal functor. I mean, a few people in the audience know what that means. These are some sort of multi-object Frobenius algebras. That's all I want to say about this. Okay. Now, for an alternative viewpoint, I mean, all this comparison to say GV functors are like Frobenius functors, like functors which behave something like Frobenius algebras, this can be made precise, and there are various people one should mention. And how can you make this precise? Well, GV categories together with these GV functors that I introduced before and certain two cells, they form a two category, and this two category is two equivalent to another two category, which I mentioned before, namely LD categories with negation, Frobenius LD functors and certain two cells. And this two equivalence behaves well under the forgetful functor to the two category of monoidal categories, Lax monoidal functors and monoidal natural transformations. Okay.
What is LD?
Sorry?
What is LD category? What is LD? LD is for what?
LD is linearly distributive category.
Okay.
Right. So this is, we have two monoidal structures which are compatibly nicely via some non-invertible mixed associators. Okay, I promised you to talk about generalizations of Hopf algebras. And yeah, so maybe the naive guess one might have is to say, okay, we have a Hopf algebra in our category of bimodules, we look at its representations, and then, well, under what conditions is this GV? But of course, this statement is nonsensical. Why is this nonsensical? I think yeah.
Bimodules are not symmetric.
Yes, bimodules are not braided in general, right? And so we need to have somehow a different notion. And okay, here's the definition of bialgebra. I think I don't need to repeat this for you. But what we will do now is we'll generalize this, and Matti has made my job easier for this, namely by looking not at bialgebras, algebraic objects in the monoidal category, but looking at, in a sense, at the functor that this algebraic object induces by taking the algebraic object and tensoring with it and looking at the end of functor on our category. Namely, we'll look at bimonads on a monoidal category. So what is a bimonad? It's a monad on our category C, which also has an opmonoidal structure. And the multiplication of the monad and the unit of the monad, they are opmonoidal natural transformations. Okay. So let me unpack this a bit. So monads pictorially, I mean, I think this is pretty straightforward. I don't need to explain it. We have a multiplication. These are diagrams in the category of categories, functors and natural, two category of categories, functors and natural transformation. We have a multiplication, a unit, associativity, unitality. And then we have an opmonoidal structure. And how can we imagine this opmonoidal structure? So we have this tuning fork, which represents the monoidal product in our category. And onto this tuning fork, we can draw this string diagram for the co-product in the way I indicated. And this is not just a pretty picture, but this can be made precise. I mean, this is essentially, these are surface diagrams for the monoidal bicategory of categories. Okay, so this is one way to, how to represent this co-multiplication of our Hopf-Lax monoidal functor. And the co-unit similarly can be depicted as follows. And then we can describe the relations also surface diagrammatically. And I said before that the problem why we can't work with Hopf algebras is essentially because we need to use the braiding, namely in order to formulate this compatibility condition between multiplication and co-multiplication, namely this Pretzel relation. And now, how do bimonads or Hopf monads circumvent this problem? Namely, you take these string diagrams and you draw them onto a surface, and namely this tuning fork surface. Namely, let's go back. So we take this string diagram and we draw it onto the left-hand surface. We take the right string diagram and pull it on top of this surface. And I mean, this is just describing in terms of pictures what the defining relations of a Hopf monad are. Okay, of a bimonad. Now we wanted to talk about Hopf algebras or generalizations of Hopf algebras. Hopf algebras can also be characterized by the invertibility of a certain morphism, namely the left fusion morphism, which I've written down here. So you take first the code product tensor with A, then A and the product. And similarly, you can define a right fusion morphism. Now a Hopf algebra is then equivalently, you have the antipode definition, but you also have the definition of a bi-algebra where both fusion morphisms, left and right, are inverted. And now taking the moral that I described to you before, you can now try to similarly define a fusion operator for bimonads. And you can do this by drawing the string diagram for the fusion morphism and then drawing it onto this tuning fork surface that I have there, this surface representing the monoidal product. Okay. So first, in terms of formulae, okay, I don't expect you to pass these formulae, but what you need to realize is, okay, this is the string diagram for a fusion morphism. We take the string diagram and draw it on top of this tuning fork surface. And this now represents a natural transformation, which we can define in any bimonad, and we require this natural transformation and the one where you reflect along one axis to be inverted. And then we call it a Hopf monad. Okay, but why Hopf monads? Well, because then the capri of modules over a Hopf monad, a bimonad, can be used to lift structure along its forgetful functor. Namely, if we have a bimonad on a monoidal capri, then the capri of modules over that bimonad carries a monoidal structure. And if we have a bimonad on a closed monoidal capri, the following are equivalent. The bimonad is Hopf, and the monoidal capri of modules, so the Eilenberg-Moore capri, is closed, and the forgetful functor is also closed. And now I come to a specific class of Hopf monads, namely these Hopf algebroids. And you can define them as a Hopf algebroid just as a k-linear Hopf monad on the capri of bimodules. And then we want a representability condition. We don't want just any monad on our capri of bimodules, but we want a monad which is given by tensoring with some sort of algebraic object. And in order to get this by some sort of Eilenberg-Moore theorem, we want that the underlying functor of our monad has a right integer. And this is a quite ahistoric definition. You can describe this much more algebraically, and this is important to realize explicit examples. But for our purposes, this is the definition that we apply. Okay. And now we come to the lifting theorem, and I think I'm ready now to give you the full statement. So if we have closed monoidal capris, C and D, we have two distinguished objects, big K and C, small k and D. And we have a functor between these closed monoidal capris, which is a pre-GV functor with respect to these two objects. What does that mean? So it's a lax monoidal functor. And we have this Frobenius form that I talked to you about before, meaning that certain morphisms made up of this form should be isomorphisms. Now, under some conditions on our functor U, namely that the functor reflects isomorphisms, so it's conservative, and the object, the small k, is dualizing. Under these conditions, the big K, the object K and C, is also dualizing. Now, we said examples of these pre-GV functors are closed monoidal functors between GV categories. So we have the following immediate corollary. So we have two closed monoidal categories. We have a Lax monoidal functor, and we have an object K such that its image under the functor U is dualizing. And if the functor reflects isomorphisms and is closed, then the big object K is dualizing. Okay. So what does this give us? Well, first of all, it shows that the category of modules over a Hopf monad on a Grothendieck-Verdier category, under the assumption that we have a module structure on our dualizing object, that this gives you a Grothendieck-Verdier structure. So, yes, sure. So this is the Eilenberg-Moore category. So T modules are for me, the objects of Eilenberg-Moore category.
So okay, again, the statement is, no, but T mod is GV.
Sorry?
If you have a Hopf monad on a category of bimodules, for example.
Yes.
So T mod is always GV, is what you're saying?
If the dualizing object has a module structure.
Okay.
Is the assumption that we need here.
If the dualizing object of the underlying category has a T module structure.
Yes.
I say any such T module structure
gives you a dualizing object.
and so makes
the
CT
same underlying object, but it might have different.
Yeah, of course. It makes CT GV.
Yes, precisely.
But if you have several, are they differ by invertible object? They should be.
This is holds in any GV category.
Yeah, any GV. So okay.
Okay. And now if we look at a finite dimensional K algebra, we look at a Hopf algebroid. And then we have a module structure on this canonical dualizing object, namely the K-linear dual of our algebra A itself.
Yeah.
Then this gives a dualizing object. And I mean, you can apply this. I mean, you have a canonical module structure on the monoidal unit. So if you have a Frobenius algebra A, so it's a symmetric Frobenius algebra, so as a bimodule is isomorphic to its dual, then you can apply this to this setting. If you have an invertible antipode, there is such a definition for a Hopf algebroid, then you can also use the antipode to get a module structure on the dualizing object. And this also gives you examples. Okay. Now you can also apply this lifting theorem to other settings. I mean, we saw that finite dimensional bimodules over finite dimensional algebra, that these gives you examples of a GV category. And this holds in more generality, namely if you have an algebra in a GV category satisfying some existence of colimits conditions, and you have additional structure on that GV category. And this additional structure is there to ensure that the left dual of the algebra and the right dual are in a good way isomorphic. So this is, for instance, true if we have a pivotal structure, meaning we have an good identification of the double dual with the identity functor, or a braided GV structure.
On where? On A mod or?
On C.
On C, okay.
And then the bimodule, namely the dual of the algebra A, and now because we have a good identification, it doesn't matter whether we take left or right dual, then this gives you a dualizing object in the monoidal bicategory and a monoidal category of bimodules in C. Yeah, that's all I wanted to say. Thank you.
Yes. Other questions?
Yeah, so you mentioned a connection between, if the categories C and D are rigid,
yeah,
between GV functors, I think, and Frobenius monoidal functors.
Yes.
What if you drop the rigidity assumptions? Is any of the implications true?
Yes, it is. And that's precisely, I think, let's go back. That's precisely this two equivalence that I sketched. So you have this notion of the GV category, as we saw before. In any GV category, we have a second monoidal product. In the category of finite dimensional bimodules, this is precisely the left exact co-tensor product of bicomodules. Okay. And then you can ask the question, how is the right exact tensor product in a GV category related to the left exact tensor product? So we need some sort of coherent morphism between them. And there is such a morphism goes under the name of distributor, then these are morphisms of the following form. So this is one, and the other one would be kind of mixed associators. Logicians call these resource-sensitive distributors, but which I find a rare name. In any case, these are in general not invertible and are required to satisfy a large number of coherences. Okay. And then you can formalize this notion, which you get, and this will give you a notion of so-called linearly distributive categories. Okay. And the categories that you get from GV categories are special linearly distributive categories, which have duals, but in a weaker sense than duals in the framework of rigidity. So you have an evaluation and co-evaluation, but these evaluations and co-evaluations mix the monoidal structures. So you have, in the source, you always have the right exact monoidal structure, and the target, you have the left exact. Okay. And then you can define in any linearly distributive category, you can define these Frobenius linearly distributive functors. And if you like, a simple way to morally define them is, okay, you have a Frobenius monoidal functor, you can draw it as strings on this associator surface in the surface diagrammatic calculus. And now what you do is you color the lines representing the tensor product so that now here, not the associator sits, but the distributor. More formally, I mean, you can take the defining relations of the defining relations and structure morphisms of a Frobenius monoidal functor and then change the tensor product so that you not always use the same one, but you use the right exact one or the left exact one in certain places. And these are precisely Frobenius linear distributive functors or Frobenius LD functors. And now this two equivalence tells you that in some sense, GV functors are precisely Frobenius LD functors.
So if both tensor products are the same, is the Frobenius LD functor just the Frobenius monoidal functor?
Yes. Precisely.
Can you again repeat the statement about functors, like properties on the functor that preserve Grothendieck-Verdier structure? Or
Yeah, like what are the conditions that I Okay, so it's
you had it on some slide, right?
Yes, I had it.
Ah, okay, this one, yes.
So first we need that the source category is closed monoidal.
But it does not mean that they are Grothendieck-Verdier, right?
Right, it's not given indeed.
Yeah. And
then the functor needs to be lax monoidal.
Okay.
And
This
is the corollary, I'm sorry. Then the functor needs to be lax monoidal. This is encoded here in pre-GV.
Yeah, lax monoidal structure plus this Frobenius structures.
Right. And then, yeah, isomorphism reflecting. And the object, of course, in D needs to be dualizing.
But dualizing means that D is Grothendieck-Verdier. You assume D to be
yes,
Grothendieck-Verdier.
indeed. Yeah.
So, okay. So it points to some Grothendieck-Verdier.
Yes.
And it has these properties of pre-GV functor. So there is such an object K in C. So together with dualizing in D.
Yeah.
And if it's isomorphism reflecting, then, okay. Then C is also Grothendieck-Verdier.
Yes. Yes. And I mean, since we discussed
kind of pulling back.
Precisely, it's the lifting kind of, you lift the dualizing object.
Right.
And
an example was this restriction functor, right? If you have
yes, for instance. I mean, that's also a stupid way to see why bimodules are Grothendieck-Verdier, because you can lift along the forgetful functor to vector spaces. And I mean, but also, I mean, this is a pre-GV functor, and now when K is dualizing, this functor is a GV functor. And by the statement before,
so this again, what is GV functor?
GV functor is just a pre-GV functor between GV categories.
Ah, okay.
And a GV functor is equivalently a Frobenius linearly distributive functor. So what the theorem tells you is that under these conditions, C is Grothendieck-Verdier, and the forgetful functor is Frobenius linearly distributed. And the other example that I motivated this with is the forgetful functor from the category of modules over Hopf monad into the category itself.
Ah, okay.
This is
so you used this result for describing for this Hopf monad picture.
exactly
Ah, okay.
because that's precisely what happens, right? So the
So
we
you
have-
so
we-
you,
we
you
add
so
extra-
you was restriction functor, right? Forgetful functor. In that
yeah,
sense.
yes, exactly.
Yeah.
That's the forgetful functor, and I mean, in some sense, that's the whole idea to me of Hopf monads or bimonads. So you impose extra structure on your endo functor so that the forgetful functor behaves nicely. And then it's just a nice, nice feature here that in the setting that we're interested in, yes, the forgetful functor indeed does behave nicely. Yeah.
So all of this is okay. None of this is linear, right? Those are
Right.
okay. If you want to do linear stuff, have you is there a way to have maybe a Grothendieck-Verdier analog for these CP rigid things, meaning that also maybe even this weak duality is just defined on objects that I would see as compact projective or something like this? Because here this weak duality, it's still defined on all objects.
Yes, that's true.
Is there a way to maybe have just a weak duality that is not even defined on all objects?
Yes, in some sense, that's what linearly distributive categories achieve for you. For instance, the category of all bimodules is a linearly distributive category. And the category of dualizable objects in the sense of linearly distributive dualizable are precisely the finite dimensional ones. So you can, one can try to formulate this in terms of linearly distributive categories, and then but this avoids the question of linearity. But yeah.
Okay, but if I in this linearly distributive categories, if I go to the dualizable objects in the sense of I could go to a subcategory.
Yes.
That is then for the Verdier.
Yes.
Right. Okay. I see. Okay. Yeah, I didn't know that. Okay. Yeah. Thanks.
There are other questions? Seems not the case. Thank you, Max. Okay, see you tomorrow.